There's a differential equation. I'm too lazy to solve it. Or maybe I can't solve it. But I can talk about what the solutions look like in the Cartesian plane just by playing some silly games. Like, for example, suppose I had a solution passing through the point 1, comma 1. What would the slope of the tangent line be? This is easy. You plug 1 in for x, 1 in for y prime is 0. There's a horizontal tangent line there. If the solution passed through 1, 2, 1 in for x, 2 in for y tells the slope of the tangent line is -1. And so the author just threw all those ticks all over the place. Is that laborious?
Yeah.
Yeah, so if you guys don't mind in Math 33, when I really get into this, I'll give you a more sophisticated way of drawing a lot of ticks at once. It's called the use of isoclines. And because I missed a day, and I decided not to go in that direction with those tidbits. Besides, if I did what the author asked me to do, I didn't do it in Math 33 anyways. But anyway, that's all that's going on. So as your solution passes this point, you know it behaves that way, locally speaking. Then move to another point and see what happens. It's that basic. Guys, before I get started on something new today, I really feel I did such a poor job yesterday. I even feel my examples were too easy. So, I'm sorry. Before I really dive into the series today, can I just throw in a few more examples of sequences? I just felt like I did a very poor job.
Can I ask a couple homework questions?
Yes, let's do that first.
We do 39 and 41 out of
Where are
8.2.
8.239.
Yeah. I was just, because normally to figure out if they're monotonic, we have to differentiate them. And like
Not
find
always,
the
but-
zeros. So I don't know if I wasn't doing that right on this one. Because they don't really have any zeros when they're differentiated. But some of them are monotonic.
Wait, you're not doing math correctly.
No?
You're not doing math correctly. What you do is you write down the problem,
Yeah.
you cry for a little bit, and then the solution comes to you.
Okay.
Exactly. It's just not Math 31, guys.
I don't mind using calculus to answer your question. I
Okay.
don't mind. It's just that with the notation the author's using, what he's really suggesting is that the nth term of your sequence is not going to be like 1.00001 to begin. I might have messed up on the number of zeros, but who cares?
Okay.
It's just that this is an exponential expression. I mean, it looks like an a to the x, doesn't it? Let's pretend x is a continuous variable. And I think if the base is bigger than 1, I grow exponentially. I think if the base is between 0 and 1, I decay exponentially. But because base is just slightly bigger than 1, I think the graph of this equation, y being equal to this base to the x power, looks like this. I'm exaggerating. It doesn't grow exponentially very fast because the base is so darn close to 1, but it does grow. That's my point. Oh, shoot, did I make a mistake? It's not x on the horizontal axis, n.
Yeah.
What changes?
Nothing.
A lot. Namely, I just get these
Yeah.
at finite value, or discrete values of x. And 1, 2, 3, 4, 5, etc., etc. But they still are on the graph that I had before. And so I think in this example, only because I know something about exponential functions whose bases are bigger than 1, I would say, for free, I'm monotonic. I'm strictly increasing.
Okay.
Now, if you want me to use some calculus, piece of cake.
Well, I was able to figure it out that way. I just was wondering if there was a way of actually figuring it out using calculus.
With or without using calculus?
With using calculus.
With using calculus, life is this easy.
Okay.
Consider the corresponding continuous function in x.
Okay.
And if I were to differentiate, it's just an exponential function, so what's its derivative?
Isn't it 1.001 to the x times the logarithm of 1.0?
Nice. So constant. Times this exponential expression.
Yeah.
It's just that now the question is, can we find critical numbers?
No.
Can we find values of x for which this thing is undefined or equal to 0? Yeah, I can't
I
either.
don't think so, no.
If I set this equal to 0, there's no solutions. This is always positive. And this expression is defined everywhere with entire reals, so there's no critical numbers coming from when y prime is undefined. Since there are no critical numbers, I get this piece is always positive or always negative. Let's figure out which. Plugging a number like, I don't know, how about 0 in for x? That's 1. The natural log of anything bigger than 1 is positive. I guess what the sign graph is really telling me about the original function up here is that it's always increasing. Therefore, from 1 on out specifically, I'm definitely as a sequence monotonic.
Okay.
So I've answered it 2 different ways.
What's the method you're using with the y prime and the number line?
I'm using calculus here. And then I answer the same question visually. But if you want, you guys, I can answer the same question with my math B skills a third way. Do you want to see it?
Let's do it.
Let's see what the relationship is between a sub n and a sub n plus 1. After all, a sub n is nothing more than this. And a sub n plus 1 is nothing more than this. But you guys are using my math D skills. Can you read that? That's an n plus 1. All right. But you guys use my math D skills. When it comes to the sum of 2 exponents with the same base, can't I pry that apart? Yeah. Is this nothing more than 1.00001 times 1.00001 raised to the pound? But now check out the relationship between these 2 beasts. Watch. Everything above my squiggly line now, everything above my squiggly line is exactly what you see inside the set of parentheses. It's just that that thing is being multiplied by something slightly bigger than 1. So I maintain what you see here is going to be strictly bigger than what you see up there. But that suggests that a sub n is less than a sub n plus 1, meaning the further and further I go out on the n-axis, the bigger and bigger I'm getting. Therefore, I think I can conclude here as well that my particular sequence is strictly increasing. So I've answered the question 3 different ways.
So, like, the next problem, number 41, is negative. So if we look at just the sign of these exponentials, is that going to be an indicator of whether they're monotonic or not? Because I noticed that all the negative ones are not monotonic. Because you're going to get different values if the exponent is even or odd.
Oh, no, wait, no, we got to back up from that.
Okay.
I wrote it down incorrectly. It's really this.
Yeah, there's no
The
preface to
principle is
it.
more subtle, so don't write this down yet. The author said, consider this. My apologies. So you guys help me with this. Let me test you on your pre-calculus days. If you consider this an x, and the graph of y equals that beast, is the graph of this beast reflected through which axis? The x-axis or the y-axis? Neither. Because I think back in pre-calculus, when it came to exponential functions, we didn't even discuss them unless the base is bigger than 1. Sorry, I misspoke. We didn't discuss those exponential functions unless the base is bigger than 0. Oh shoot, look at my base. It's not. It's negative. So I think I have to be more careful in really discussing the monotonicity of this particular sequence. So if you don't mind, I'm going to play a silly game. Here's my n-axis. Here's my y-axis. Please do not be careful with your arithmetic. Be really sloppy. If n is 1, isn't that just a negative number? If n is 2, isn't that some positive number? And if n is 3, oh shoot, it's negative again. Do you guys see what's happening? I'm actually popping back and forth from positive to negative as n increases by 1 every single time.
And it still converges to 0?
I think it still converges to 0 for these sloppy hands. Because if the negative sign weren't there, I'm still exponential with a base between 0 and 1. I know I'm exponentially decreasing down to that horizontal asymptote on the, if I can call it this, x-axis.
Okay.
It's just that since the base change has a negative sign in there, I'm changing signs to the output for every increase of 1 unit for n. Therefore, I'm oscillating back and forth. So everybody, in this example, am I monotonic?
No.
No, I'm not strictly decreasing or strictly increasing. Do I converge?
Yes.
Yeah, to what do I converge?
0.
0. Now what do I converge to?
3.
3. I'm just shifting everything up 3 units like that. Bradley, I don't mind.
No, I think that might be it.
that was number 41.
Bradley, that was number, no,
Yeah,
42.
40.
42.
Or, yeah, no, I think that was 41.
If it's
Or
41,
is
I
that
changed the
42?
number of the base, but it's okay, it's the same
Okay,
thing, same
okay.
answer.
Okay.
On 58, I just want to be clear, when it doesn't specify epsilon, do I solve for n in terms of epsilon? Or make one up, or,
In number 58,
yeah.
well, I think in number 58, if you're going to prove this is a true statement, you want to show it's true for all epsilon strictly greater than 0. Do you want to see me go through it?
Well, is my final answer going to be n is greater than something epsilon?
No, your final answer is going to be yes or no.
Okay, then yeah, I'd like to.
All right, all right. So the limit of 1 over n squared as n increases upbound is equal to 0, but the author wants me to actually prove that this is true. Now let me go back to my definition. I think to say, by the way, you guys, this is a man-made definition. This is the theorem. It's a definition. Whenever I make the proclamation that the limit of the nth term of a sequence as n increases upbound is equal to some fixed real number called L, it simply means no matter what epsilon is, there exists a corresponding number n such that in absolute values, the difference between the nth term of my sequence and that limiting value L is going to be no more than epsilon whenever my little n is chosen big enough. In other words, at least as big as big N. Do you guys want me to draw a picture before I go through this? Do you understand the definition? And be honest. All right.
Just, can you collapse the tables?
Yes. Sort of like saying this. If this is really a true statement, if it is, you guys, doesn't that mean this? Here's my n-axis. Here's my y-axis. Can I draw on y equals L real quick? You guys, in words, I'm not going to do the epsilon garbage yet, nor the big N. I'll do it in the 15 seconds. What does this mean to you on an intuitive level? What does it mean to you on an intuitive level that this is a true statement?
That it curves up to L, but it never passes.
Curves up to L, but could it pass it?
Could.
See, I think could just make sure you come back down. Or maybe overshoot it and come back up again. Or maybe oscillate back and forth. I just think what this really means is this. N is equal to 1, to 2, to 3, on up. I think the corresponding points in the graph of this particular sequence, when y is graphed against n, simply means my particular a sub i's are just jumping all over the place. It's just that eventually, if the limit of a sub n really is equal to L, eventually, I hone in on L, don't I? Intuitively. But if that's my intuitive interpretation, let's look at it a little bit differently. I think if that's really true, then no matter how small epsilon is, if I deviate from L by no more than epsilon units, again, epsilon being some small positive number, no matter how small epsilon is, no matter how slender this band is about y equals L, the limit of a sub n really is equal to L. I just simply means eventually on the horizontal n-axis, eventually, I'm going to get a sub n's to be no more than epsilon units away from L. I know I can't draw you guys, but make sure you look at my color. Do you think then I can proclaim that this is my n right here, my big N? Because now for any term a sub n where little n is bigger than big N, it is the case that my a sub n, that's little n, is no more than epsilon units away from L. Do you guys agree?
No.
No, why not?
You still got another point on there.
Oh yeah, look at that blue point. I think here's a value for little n, for which the difference between a sub little n and L is bigger than epsilon, isn't it? Shoot, I'm not in that horizontal band. But if this really is a true statement, you know what? I just need to go out further. All right, I'll cross that big N out. According to my picture anyway, how about big N being here? Now I think for all little n's, hold up, I misspoke. I meant to say, if little n is at least is bigger than big N, then it necessarily is the case that in absolute values, my a sub n deviates from L by no more than epsilon units, which is exactly what that definition over there really says. Do you guys agree? Sir, I never answered your question. I'm sorry. I'll come back. So let's come back. First things first. Let's find, and then that works. In other words, given an epsilon greater than 0, we need to find an n such that in absolute values, the difference between a sub n and L is no more than epsilon units whenever I choose n big enough. But you guys, look at carefully how I'm wording everything. I'm saying, given an epsilon greater than 0. It's sort of like my boss is opening that door and screaming at me through the door, saying, I need you to get your job done. I'm manufacturing ball bearings, and I need you to make sure on your machine that you create these ball bearings with a fixed volume of 1 cubic millimeter. But if you deviate from that desired L value, which is the volume of that particular ball bearing, by more than 10%, you're fired. And I go to my machine, and I see there's no calibration tools on the machine to make sure I get a particular volume. It just tells me that if I produce enough, then, say for example, the volume is close enough to what I want. And so I don't get fired, I need to find out how far I need to go with my machine, how many to produce, so that I get that desired accuracy. I don't know if that's a good analogy. But, check this out. I guess that means that my a sub n is just 1 over n squared. My L is
Yeah.
But this difference is just this. You guys, I'm running out of room. Can I cheat a little bit? If n goes from 1, 2, 3, 4, 5 on up, isn't n always positive?
Yeah.
Oh, maybe even if it isn't, I'm scoring still a positive. I think I've got the right to suppress my absolute values. And now multiplying by n squared. Dividing both sides by epsilon. Taking the square root of both sides. I said dividing by epsilon.
Yeah.
Didn't I? Jeepers. But taking the square root of both sides. You guys, my algebra okay?
Mhm.
You might have said my algebra is not okay because maybe from here to here it's not quite legal in the sense that I don't know if n's positive or negative in general. And so algebraically speaking, I've got to worry about that. Besides, taking the square root of both sides, I've got plus or minus components. But, again, you guys, since n's going to be 1, 2, 3 on up, I don't have to worry about it. Now, every day my boss opens a door, he's screaming at me a different epsilon value. And so I want to find my big N that relates back to epsilon so that every single day I don't get fired. But you check out what I've just accomplished on the board. Watch. I think big N is a lower bound for little n. But this thing is a lower bound for little n as well. And so why not, for convenience, just choose big N to be that expression in epsilon. So every time he screams at me open the door, I can give him a corresponding big N that's in terms of whatever tolerance value epsilon he gives me. So I think what you and I need to do is choose. Our big N to be, I forgot it, 1 over square root of epsilon. Now you guys look at that middle board. Can you really appreciate what I've just proven? What have I proven?
Nothing.
0, nothing. All I have in the middle board is some scratch work at what big N really should be. So let me come back over here. I know I wrote this as my formal definition, but when you look inside the set of premises here, I think that could have been stated differently. I think I can state that as a conditional statement. I think with that keyword whenever simply means that if n is chose sufficiently large, then the absolute value of this difference will indeed be less than epsilon. I should put the word then in there, excuse me. It's an if-then statement. And if you guys don't mind me using a second version of my definition over here, let's deal with it. So part 2, let's show it. that this particular choice for n works. And so everybody, here I go. Let's start this off legally. Given an epsilon strictly positive. If n is strictly positive, then maybe we can take a break and find a better pen. Ooh, we're back on track. So given epsilon greater than 0, let's choose our n to be just that, 1 over square root of epsilon. Now you guys, if I'm really going to prove the limit of 1 over n squared really is equal to 0, that means this. Making the supposition that little n is at least as big as big N, if I can show you, the reader, that an absolute value is the difference between a sub n and L is well, eventually, yeah, less than epsilon, then I think by definition, I've proven to you that the limit of 1 over n squared is equal to 0. So let me just run through the basic math algebra. A sub n is this. L is this. That difference on the inside of the absolute values is this. But at this point, my absolute values are superfluous. It's just that when I take a look at 1 over n squared, let's go back to my supposition. If little n is bigger than big N, then isn't 1 over n squared going to be less than 1 over big N squared? You guys be honest with me. Is my math be okay? No tricks. Okay. Because I don't mind math questions. Oh, wait a minute, hold it. We chose n to be this, so I guess I can make a substitution. I'll replace my n squared with, well, what I called it, which is 1 over square root of epsilon. But jeepers, isn't that just simply epsilon? Now let's come back to what I did logically. I made a supposition that n was at least as big as the big N that I chose up there, and look what I've concluded. As we've had a difference is eventually strictly less than epsilon. Therefore, I'll make my proclamation. It is indeed the case that the limit, as n increases that bound, of 1 over n squared is equal to, I've lost it. 0
0,
itself.
yeah.
I agree. That was my L. You guys, what do you think? Can you guys give me a show of hands if you're going to be this quiet? Seriously. Give me a show of hands if, even though you might have failed to understand it, give me a show of hands if you think your Math 30 or how one professor gave you sufficient practice with this.
You actually assigned these problems to us last semester.
Yeah, you guys had a horrible professor. So.
Yeah. Giving us infinite limit proofs in Math 30.
Sir?
I've ever taken them again.
You asked, okay.
Me?
Did you ask this question?
Yeah.
Okay. Is that okay?
Yeah.
I just don't know if that's what you expect.
What was the original question?
The original question, Tyler, was this: prove that's true. And I should say, using my definition of limits with sequences, prove that statement's true.
Wait, so at the end, how did you get back to 0? How are you saying it equals 0 at the end?
Here's how I did it. It's because that is my a sub n, and that is my L. In fact, you can even see I put them in over here. My a sub n, my L. And once I found the absolute value difference is strictly less than epsilon, given this supposition, then I know that the limit of this beast is equal to that beast as an increase up down. Or say it over here, I meant to say the limit of this beast is equal to that beast as an increase up down, just by my definition. You have to tie things together over here. Watch. This in true means all this. So to prove that this is true, I've got to actually show that if little n is bigger than big N, then this is going to be a true statement. And if I can succeed in proving that, then this particular statement is true. My L in this example just happens to be 0 itself as a number. But there's a lot there, and that's why I asked this question. There's a lot there. If you guys didn't have a lot of practice with this back in Math 30, although your definition for limits is a little bit different, they involve deltas, not big N's.
At Sac State, we never went over proofs.
Then how did you define a limit?
They just told us this is what a limit is, and this is what you need to know on the test. Like I've never seen this before.
How many of you have never seen this before? I'm not gonna yell at you, I'm not gonna get upset. Wow. You know, in some subfields of mathematics, this is all it is. Some people can interpret topology as being like this, to study these balls, these neighborhoods, these delta neighborhoods of certain points. You guys, do you remember back in ninth grade high school algebra? You said the natural numbers are the counting numbers, 1, 2, 3 on out. Integers are those things, they're negatives and zero. Rational numbers are numbers that can be expressed as ratio of integers, which by the way means fractions. And do you remember how somebody described to you what the real numbers are? They said, oh, the real number is a collection of rationals with the irrationals. That's a lousy definition. We've lied to you this whole time. We've never given you a definition of real numbers. In fact, you won't see one, even here at Sierra College. You have to study real analysis beyond the scope of this college, and it really involves so much, including this notion of these delta neighborhoods. It becomes so important in mathematics. You can't define the real numbers without it. It's that important, I don't know. For some of us who are going, and so I'm serious. I just can't jump up and down saying, this is a big deal. In fact, I think that's probably the most important thing you should have done myself.
I have a question.
Yes.
There's this P.
Sorry, I didn't mean to run them up with that.
There was this P. What does a P mean? Like a capital P, like an epsilon deal? Or not epsilon,
Oh, is it row?
is that what it is?
Yeah, just when you find it, show me what page you're on.
It's, we're just looking at it, 8-1.
It was A3, I think? Or was it A2? I think it might have been the end of A2. So I think it was on this page right here. And then,
There it is, page 548.
Yeah.
540H?
Yeah. Number 79.
Oh, sorry. I see. That's pi.
It's what?
The Greek letter.
Well,
Pi.
what?
Well,
Well, why is it used as a sigma notation?
well, look at that one. That's simple. Lowercase pi. What does that represent?
3.14.
No, what's pi?
Something to do with the circle.
Yeah.
It's the ratio of the circumference of the diameter, right?
For what circle?
In a circle.
Any circle. Now, Dave, you said 3.14. That's just really an approximation. But now you're talking about a big Greek letter P.
Yes.
What about the lowercase letter s or sigma? What do we typically use that for? Standard deviation. Well, statisticians stole that for standard deviation. But I like the letter s to represent a sum. So I steal the uppercase Greek letter sigma as I arrange from 1 to n of maybe some a sub I as being the sum of a sub 1, a sub 2, all the way up to a sub n. Likewise, if I got the product as I arrange from 1 to n of an a sub i's, or the a sub i's, I think it's just a sub 1 times a sub 2 times dot times my a sub n. It's just a convenient way to represent a big product. That's why we choose the letter pi or p in the Greek alphabet.
Isn't that the same as
But it's the uppercase letter.
I forget what it's called, but it's an exclamation mark.
Oh, factorial.
Yeah.
Yeah, it's just the factorial is a specific example where I'm working on the natural numbers, and it is the case that each and every one of these entries is decreased by 1 unit. Yes. I'll discuss that today. And when it comes to factorials, you guys, let's do it. Let's take a break. 5 factorial doesn't mean scream it out loud. It means we got.
5 times 4 times 3 times 2 times 1.
And so n factorial is nothing more than all the way down to 3 times 2 times 1. Now, for you guys this semester, the downside of the factorial function is you can only evaluate numbers like 1, 2, 3, 4, 5 up. It's got to be a natural number. But this factorial function coincides with another function defined over the reals. Somebody know what the function is? Think Greek. What was that? Yeah, the gamma function. It's a continuous function, but if you restrict it over this restricted domain of the natural numbers, it coincides with the factorial function.
Are we supposed to know the gamma function?
No, just
Okay.
just curious. It's a really interesting function. I remember when I was in graduate school, I'm so old, CDs just came out. And I found a CD that had the gamma function mathematically modeled on it. So I took it, I put it in a CD player, and I hooked it to the oscilloscope and to a stereo system simultaneously. It's so cool. See how the gamma function changes. You gotta do it sometime. A lot of fun. Sorry, I'll come back. You guys, anything else in the homework? Does that mean you're ready for the quiz?
Good.
You guys